In this video, I'm going to implement image-to-image generation using stable diffusion. So the basic generation with classifier-free guidance is summarized by these three functions here. This comes from lesson 9, lesson 10 of part 2 of the fastai course. I go into more detail in the negative prompting video, but I'll do a brief overview of what goes on here. So make samples is really the main function that we are using to generate our images. We start by giving it our prompts and optionally a negative prompt, which defaults to the empty string, so our unconditioned prompt. We pass those prompts to the text encoder and we concatenate them so that we have a single tensor that we can do a single forward pass through the UNet with. We generate our noisy images, our noisy latents, and then given however many time steps we chose, that's also one of the arguments to this function is the number of inference steps. We run through the diffusion loop, and once that's done, we decode our latents with our VAE, and we use this make image function to transform the image to a pill image, and that gives us our result. So I'm going to run this prompt using this generation process. So a dancer wearing a colorful dress, and this is the prompt that I'm going to use throughout this notebook. And what we'll see, hopefully it should be the same thing that I ran before. What we'll see is this dancer with a very colorful dress. Yep, this is the right one. And you can see that, they have, yellow-green dress and this like magenta looking thing, and there's a cityscape in the background. So this is going to be our baseline image that we're going to compare other things to. But image-to-image generation is not starting with a random set of latents. It's starting with a particular image that you want to build upon. So I'm going to use the image that they use in the course. And this is going to be this macaw. Very, very cute, very beautiful macaw. You can see very vibrant, so that's why I chose a dancer wearing a colorful dress, because I thought it would draw upon some of the bright color in this image. So that's my macaw. If we look at the values in the image, we'll see that they go from 0 to 255. Okay, so that goes from 0 to 255. And what we want to do next is we want to transform this to a tensor so that we can pass it into our VAE. So we're going to use the same code I used up here, so I can reuse it later in a function. We open our image, we convert it to RGB, then we resize it to 512 by 512, and then we make sure it's on the GPU and it's half precision. Now if we look at the shape, it should be 3 by 512 by 512. And then if we look at the min and the max, we'll see that this is now between 0 and 1. So we've kind of, instead of 0 to 255, it's more similar to a float where the image kind of intensity, the pixel intensity is between 0 and 1. So we have everything we need to now encode our image into latent space. So I'm going to do that in this line of code. And I'm going to take my initial image. I did find that I have to, I have to unsqueeze it. Unsqueeze the first dimension. Oops. And then I have to multiply by 2 and subtract 1 because I want to go from 0 to 1 to -1 to 1. So I want to slide that range of pixel values because that's what the VAE is expecting. And then I'm going to access the latent distribution, take the sample, and multiply it by the latent factor or the VAE factor. And this should be now in latent space, which it is. So it has 4 channels now instead of 3, but each of those channels are 8 times smaller. So we went from 512 to 64. And if we look at this particular input, so I'm going to look at my transformation here, and if we look at the minimum and the maximum, we'll see that it's between -1 and 1. Cool. So that prepares my noisy, or sorry, not noisy yet. These are latents for my regular image. And now I want to add noise to that image. So the first thing I have to do is I have to decide how many inference steps am I going to use, and I'm going to use 70. Then I have to set the scheduler for that amount, because I can use different amount of number of steps for inference, and so I have to set the scheduler to so that it appropriately adds the right amount of noise at each step. The next line is the most kind of central line to this implementation, which is this initial strength, and so this is basically going to determine how much noise I'm adding to my macaw latents. And I think of this as, kind of I'm pretending that I'm starting, I started with random noise, and then at 15% of the way I'm going to inject this noisy macaw as if this was what was generated in the diffusion loop. And so we're going to vary this init strength at the end to see how that affects the generated output. So my initial step is just the integer of initial strength times the total number of steps. And for this one, it's 10 steps. So my diffusion loop will only run for 60 steps, because the first 10, I'm kind of pretending that the first 10 went into generating this noisy macaw. Those are inference steps. We have to convert those to time steps, and we use our scheduler for that. And okay, that looks good. And then a couple of other parameters, the batch size and the manual seed, because I want a particular output for my random latents. And then now I can actually apply, or actually create the noise, and then I'll apply the noise. And the shape of the noise is the same as our macaw latents, so that's a good check. And the last thing in this step is to use the scheduler and add noise. I'm going to give it my macaw latents, I'm going to give it my noise, and the time step that I want to start with. And this will be the same size. Okay, cool. So now we have our initial latents that are a noisy version of macaw latents, and we've added noise in such a way that it's 10 steps into the diffusion process. So I'm going to set my prompts as a dancer wearing a colorful dress. I'm just going to have one prompt. My guidance scale is going to be 7.5 because that seems to work really well. My batch size is the length of prompts I have, which is just 1. I'm going to encode my text. So I'm going to encode my prompts. And then I'm going to encode my, this should be this. I'm going to encode my unconditional text, which is just an empty string, repeated batch size times, and it has the same shape as my conditional text. And I'm going to run this, and it should be the same size, which it is. So we have one batch, or one item in the batch, 77 tokens, and each token is projected out into 768 dimensions. Great. Last thing I need to do with these embeddings is I need to concatenate them. And we're going to do just that. And check the shape. It should be 2 times 70 times 768, which it is. Okay, cool. So now I can run the diffusion loop. And I'm going to write that out here. And we're going to start the kind of key difference here, actually the only difference here from regular diffusion is we're going to start at our initial step. That's it. Everything else is going to be the same. So I'm going to go up here and I'm just going to copy these lines. And instead of returning my decode, I'm going to save it as a final image. And just to look at this line by line, I'm going to prepare my latents, and what I'm going to do is I'm going to multiply or repeat them twice because I have my concatenated text embeddings. Then I'm going to actually run inference on the UNet. It's going to give me back the noise estimates. I'm going to use classifier-free guidance using my guidance scale of 7.5. And then I'm going to remove the noise estimates using the scheduler step method. And once that iterates through 60 times, I'm going to decode it, my final latents, and then I'm going to get my final image. So if we run this, we should see that it runs, only 60 times. Okay, so now if we run this, this should look a lot more similar to our macaw, which it does. And this is what I expected, given that I ran this code before. So if we go back up here and we grab our macaw, and let me zoom out a bit. So we can see that we can sort of see the wing shape in her dress. And we start here at red, blue, green, yellow, back to red. And that matches the red, blue, green, yellow, red pattern. And we can also see this kind of angle inclination that the dress has, which the macaw has as well. Okay, so this confirms that we were able to generate an image using an initial image, and we started at some arbitrary point of 15%. The next thing I want to do is I want to vary my initial strength parameter, and the reason I want to do this is because I want to visualize, how this directly affects the output. Something that I really like to do when I'm running stable diffusion code is I like to, wrap the code in a function, which is already done for us in fastai, and add a couple factors or some kind of parameter, something that I can tweak, and I can run through maybe 20, 40, 100 times different values and then create an animation, because that pipeline is really simple to create a simple GIF animation. And I find that it's really satisfying and really informative because it's such a visual operation. You can really see exactly how your parameters are affecting the code. So I'm going to grab my make samples function, and I'm going to add a couple parameters. I'm going to add initial image path, and that's just going to be our macaw for now. And then the key parameter is initial strength, and that's the one that I'm going to vary. I'm going to modify the noisy latents generation because that's the main thing that changes. So first I'm going to load the image and encode into latent space. So I'm going to go here and grab these lines. So this will load the image. And then I'll go back up here and grab this line, which is going to encode it into image space or latent space. Then I want to add noise to the image latents. So I'm going to do this first. I'm going to set my time steps. I'm going to grab this guy here. So this is going to give me my initial inference step. And this is going to give me the corresponding time step. Instead of being my original latents, this is going to be noise. And I want to make sure this is on CUDA because the initial image is on CUDA. So this becomes our noise. We're going to remove this line here and we're going to replace it with this line here. So just recapping, I set my seed so I can check that it looks the same as I have in previous code. I'm going to load the image based on the image path, and I'm going to encode it into latents, and then I'm going to create some random noise given this shape, and then I'm going to add noise given my macaw latents, the noise, and the time step. And the time step is based on the init step, which is based on the init strength, and this is a parameter to this function. And the only change down here is going to be that I want to start with my initial step. So I don't want to start at 0, I want to start at, in this case, 10. And I think everything else should be the same, so we're going to do that. And so now, instead of doing one image, I'm going to do 40 images. And let's do this. And then the images are going to be the output of make samples. I'm going to give it the prompts that I defined earlier. Everything else is going to be the same. So I'm going to keep a blank negative prompt, so it's an unconditioned text. I'm going to keep the guidance scale to see the number of inference steps, the initial image path. The only thing I'm going to change is initial strength. So I'm going to do initial strength here. And this is going to be the loop iterator, or loop index, times 1 over n. So 1 over 40 is 0.025. And I is going to go from 0 to 39. So this will go from 0 to about 99%. And once that generation happens, I'm going to pass it through my make image, and I'm going to append it to my images list. And then I'm going to use that list to make a GIF. So let's run this, make sure it goes, and then I'll skip to the end. Okay, great. So we can see that a very nice visual check to see that the code is working, and we're going to obviously look at the output. But a cool visual check is that we can see that the number of inference steps is going down as initial strength goes up. And that's because the init step value is increasing with init strength, and so we're starting later and later in the diffusion loop process, so we have fewer and fewer steps until we get to the final image. So that looks great. I'm going to now save this as a GIF. And I got to give it this save all parameter. And then append images is important because this tells it which images from the list, so it's the rest of the images. And I'm just going to do 100 milliseconds, and I'm going to do a loop of 0. So this should take a few seconds to run. While that's running, I'm going to import this method so it's easier to view. and that looks good. So the very first image is dancer with a colorful dress with no noisy macaw. It's just pure noise. And then the last image is where, we have pretty much 99% initial strength. And so we have pretty much noisy macaw is our starting point. And then we do like 1 or 2 steps, diffusion. And you can see how the dancer starts with their hands up. And then as we get further along the init strength parameter, the dancer's arm starts wrapping around their head and their body tilts, and you can see the transformation to align the dancer's body with the macaw's body until at the very end the dancer's transformation into macaw is fully complete. So I hope this was like an interesting and enjoyable walkthrough for image-to-image generation. Thanks for watching. Leave any comments below. I'm going to put in the video description my blog post that walks through the step-by-step process, and I'll also attach this Colab notebook in the video description as well. Awesome. Thank you.